we ready? Oh, okay. Oh, thank you. Okay, so we are going to start slow and big picture. All right, we're going to start out here about why we're doing this, what we're trying to accomplish, and we're going to narrow in very quickly. We're going to narrow in, and then we're going to get very specific into models. The way I run the course is I'll give you just enough equations to explain and keep you on track of what we're doing, but I won't overemphasize the equations. They're in the book. I'm much more interested that you know what the equations mean and how we interpret and how we understand the things we're doing. The comprehension, the understanding part is far more important than being able to write an equation for me or memorize an equation or anything like that. So you've got notes. What I want you to do as we go along, and even before we start, I bet a lot of you already have a list of questions you have about statistics and modeling. So I encourage you, if you already came to this class with questions about wanting to understand things about models and why you do certain things in models and statistics, write them down. Make sure that when you leave this class, you have answers from me on those questions. As we go along, please write down questions that you have. When I say something that you go, oh wow, why do you do that? Write that down and make sure you ask me, either in the class or in the break, and you come up to me one-on-one and say, why do you do that? Okay? I want to make sure you get your questions answered so that your understanding of modeling and statistics is better when you come out. So if you don't ask me those key questions, then you're doing yourself a disservice. All right? So what is a model? Seems like a silly question. But model is, we do this, when you all go to the, when we travel, and I travel, I love to travel, and I've been loving my trip to, this is my first trip to India, by the way, and absolutely loving it. And I have to say, I told Sudeshna this morning, I did a bicycle tour of Old Delhi and when I got there, and it was about 10 of us on bicycles, and we went through the old little streets of Old Delhi. And there were 3 Indians on our tour that live in Delhi that had never done it, along with about 7 of foreigners that did the tour. And all of us were absolutely changed our lives forever. Amazing, most amazing, incredible experience in the heart of Old Delhi, seeing the markets and seeing the madness and absolute chaos that unrailed there. But if you go to Australia and you're in the airport, you can get a little or a stuffed animal of a koala bear, right? As you leave and a lot of people get those as they leave. That koala bear is a model. That koala bear is a model of a real koala, right? The ones that people pay more for look more like a real koala than the ones that are cheaper, right? So the companies that do a better job of providing a model of a real koala can charge a higher price. But at the end of the day, whatever you buy, whatever you choose, you're not going to get a real koala. You're not going to get the real thing. That's like a model. At the end of the day, when we develop a model of something, a statistical model, we're not going to get the real thing. We're going to lose some of the complexity of the real koala. We don't have a beating heart. We don't have the circulatory system. All we get is the outside, actually. So the thing you buy in the shop of the koala is actually a pretty poor model, depending on what you want to know about it. It doesn't have a lot of complexity. All it has is the outer core, which is probably the simplest bit of the whole koala. So in modeling, it is a representation of reality, but it misses complexity. Just like the koala that you buy in the tourist store, it's not the real thing. Often the model that we buy is we're trying to use it to learn something about the real thing. Okay, that's why we develop models. But it's really important to remember that it's not going to be the real thing that we're doing. A model that fits the data well is not necessarily a good model. Take the koala bear example. It may look exactly like a real koala, but nothing inside works. So actually, you could argue that if you're trying to learn about what a real koala is like, that one you buy in the shop is terrible. But it looks really good. Same thing when we get into the math. Same things when we get into the statistics. We can get a model that fits the data well, but it actually doesn't inform us. It doesn't capture the complexity that we want to capture. So that's really our charge in modeling, is how do we develop a model that is good at capturing what we want to understand about the process. It can completely fail to capture the important bits. The problem is we often don't know when we're doing model. We have to be really, really good scientists to know and to question ourselves to know if we are estimating or we're looking at a bad model. And there are a number of things we'll do to try to help us. But that's what a good modeler does, is knows when a model is not capturing the right complexity and is not doing a good job. You all know this. We're talking about the models on the right-hand side here. We're talking about models where there are uncertainty, not the left-hand side that are deterministic processes. So everything in this class is going to be about models where we don't know for certain the value of an outcome before it happens, and there are parts of a process that we know we won't be able to explain or understand. So, to sum that up, it's the art of modeling or describing a system, process, or phenomenon in light of uncertainty. That's what we're trying to do. What's the process? Why do people engage in active travel? How do intersections work or not work? What causes delay at intersections? What causes crashes at intersections? Why does pavement rutting occur? And there are all kinds of really interesting questions, and I hope that we end up talking about some of those in this class, as some of you bring examples and say, hey, what about this data set? What about this problem? And we'll talk about that, because that's where all of the interesting information is. So let's talk for a minute about where does all that uncertainty come from. I'll tell you right now, as we get into the model, what you'll find out is that, let me back up a couple slides. Often, what is most interesting about a model is not the line that we fit, but is what is in this error term. What's going on in the errors? And that seems weird as a statement to make, but it turns out to be true. And as we go down this class, you'll start to see, we'll go, wait a minute, what's in that error term? What's happening here with the error terms? What do we have? So I'm going to talk to you now about what actually is in the uncertainty. So there's a bunch of things that add to the uncertainty of processes when we measure data about a process. And a bunch of them are listed here. We don't measure things perfectly. Household income is a notorious one that we don't measure well. People don't like to give precise information about their household income. They would be happy to give brackets, and so we don't measure that with great precision. There's interference. How much money would you give to save the koalas? I would give lots of money. The koalas are beautiful animals. Well, in certain types of questions and surveys and certain types of information that we get, people don't give necessarily the most honest of answers. And so so sometimes in survey data, for example, we might have bias built in depending on what questions are being asked. There could be also bias because we don't know all the people. If we're asking surveys, for example, people don't have all of the information necessary to give a good answer. And we'll have examples of that in the class. So we can have a bias that comes in the responses. This number 3 here is probably the biggest one where research falls flat and goes bad. In Australia, we have this expression called when it goes pear-shaped. I'm sure they don't use that here, but in Australia, if you're standing somewhere, I had to learn all the lingo when I moved to Australia, but they say it went pear-shaped, and I thought, what do pears have to do with it? But pear-shaped means it's gone bad, and often that's because there's something really important in the process that you're trying to model but has been left out of your model. And that, as we'll see, can cause really big problems for us. Big problems. We'll talk about more of that later. We can purposely omit known factors that will affect the response. It's also bad for us. And create what the theory or some loose theory says about what we expect to see and what the theory doesn't know, what we're trying to find and learn new about some process, or why something's changed and we need to look at it in a different light, or because they've studied it over there but they've never studied it over here and maybe it's different over here. So we need to understand the process really well. That's the starting point. And we should have some even if we don't write it down, it's good to write it down, but even if we don't, we should have some concept of what you expect to see. So, if all of you, a lot of you doing research, doing PhDs, you should all be able to, if someone calls you up in an elevator or in front of a classroom and said, what do you think your model, what do you expect to see? What do you think is going on in your process? You should say, well, these are the factors that affect cracking and pavement performance. These are the factors that influence people to not walk or ride a bicycle to work. These are the pedestrian infrastructure challenges, and this is why we can't fund this infrastructure, etc. We should have an understanding without any statistics, without any data. That's our responsibility as being a good researcher. That's the starting point. Then we collect data around that to answer the questions and the bits of the process that we don't understand. And then we'll develop that model and develop sophisticated models to understand what's happening. So the process, yes?
But ultimately from the model we may not find it, and then statistically.
Yep. Yeah.
And then something which we collected thinking it may have some effect may also end up having significant effect. So what would you say for in that context, right? The theoretical and what you find from the model.
So it's a great question, and so the theory is to help us to actually articulate the questions that we want to answer. This is what we know about the process, and often the argument goes something like, this is what other people have done and what we understand about the process. However, there's still this little bit of the piece of the puzzle that we don't understand, and there might be some possibility that these things affect Y that haven't been explored before. Or what they think they did before about these X's or these factors that affect Y, we don't think they've done really well because of A, B, and C. Then you go down and collect data and you do your experiment. You may find out in the end that you were wrong, that actually what they did before was sufficient, and that's really, really useful information. And there's this idea out there that if we don't have statistical significance, that it's a failure of the process, and we shouldn't report that. But actually, we should. In fact, in papers, it's just as important to identify the things that were not significant as the ones that were, because both are pieces of information in the process. And so we don't always get it right in the theory process. That's the part of experience. That's what research is we're trying to discover new things, and sometimes we do, and sometimes we don't. So it's very important that we convey both the things that turn out the way we thought and the things that didn't. Although the literature is not as evolved on that, and I think the really good journals are smart about learning that and valuing that. So let's start talking about getting a little more specific here as we go down. So we have the research questions. We usually turn those into hypotheses. We think X1, X2, and X3 influence Y. We think whether you stayed out last night does influence what mode choice you're going to make, et cetera, et cetera. And we're going to test those kinds of things. We then look at the theoretical models. What do we think they should look like? We'll collect data or have data or whatever else to do that. We'll then conduct an experiment or quasi-experiment or observational study. And then we'll do the analysis techniques. We're going to spend almost all of this class on the very last box. Okay? So we will kind of skip and go very quickly through all the first bits of this flowchart. But I want to point out here that all of these bits of the flowchart are so important. We just aren't going to focus on them here. We're going to spend most of the time on this. But it presupposes that all the right stuff has been done up here, and that we understand, and people have done a good job of collecting the data, designing the experiment, and doing all those sorts of things. So, but if you want to ask questions during the class, in some of the data sets that we have, so we'll have data sets and we'll be analyzing, we'll be back doing this. But if you want to ask one of the questions that might tie back to here, do so. Why did they include that variable in this data set? That would have been something answered way back up in here, maybe in the theoretical model or the research hypotheses. Ask the question. We can have those discussions. But all these other parts are really, really important. But unfortunately, we can't spend a lot of time on those bits. So real quick before I leave that one, we should all recognize that there are really three kinds of designs and experiments that you could add another one here. You could add time series as a longitudinal one. Usually they're differentiated, but I don't want to talk about those for a second. Because they have really important implications to everything that we do. So let's define them first, and then let's come and talk about them for a second. What are cross-sectional data? Anyone know what we would refer to as cross-sectional data? Anyone take a stab at that? So cross-sectional data are just where we just observe a bunch of entities, whatever it is, households, pavement sections, at one point in time or in one sampling period, just a bunch of different locations. We observe them once, each site or household, whatever gets in the sample once, and we call that cross-section. That means that kind of what the word cross-section comes from is we just take a snapshot in time, a cross-section of the population, boom, one-time shot. And then the next type are longitudinal. So longitudinal would, for example, be two cross-sections of the same people. So over the same households or the same pavement sections or the same footpaths, the same bridges, whatever it would be. You do them once, and then you wait a period of time, and you come back and you measure them again. And that would be definition of a longitudinal. You could do a third time, a fourth time, a fifth time, But if you have more than one, we call that longitudinal data. Before after is a special case where we have two observations, a cross-section before, we come in and make a change, and then we have a cross-section after, right? So the importance there, usually the change in the longitudinal is just happens, we record it, but it's not controlled in any way. It just happens. So we observe households. So I've been involved in a study in Brisbane, for example, where households are surveyed every two or 3 years, the same households, and they've been doing it for 15 years now. So we have 7 or 8 cross-sections of the same household. Bunch of stuff changes. Some households move location. Some households get new cars, sell old cars. So a lot of stuff changes from period to period. But the before-after is something where we usually go in and purposely make a change. So time series is usually when we have lots of high-frequency observations of something. So we observe households every day for a year or every day for 3 months. We observe the pavement performance cracking every day for a month. So we just have very, very tight, and that's usually what we would call a time series. Okay. Let me say one more thing about cement one idea about before I move on. The reliability of these data, of your models and everything we say depends on the type of data that we collect. The least reliable data are cross-sectional data. Probably the most reliable would be, well, they get more reliable if we observe them over time. Longitudinal data become quite reliable because we observe things over time, and before-after data are quite reliable because we actually come in and experimentally control things. But here's what I want to I'm not just going to make the statement and then move on and expect you to believe me. I want us to understand why I make that statement, that cross-sectional data are not as good as the other ones. Does anyone have any idea why I would make such a statement, that cross-section data are not as reliable or as useful as something that, let's say, I measure households over time. So let me just paint a specific example. I measure a household, the travel making of households one time, and that's the sample I have, versus I measure the travel of households now, and then in a year from now, I measure the same households. Same variables. Why is cross-section not as good as the longitudinal, is my question. Does anyone want to?
You might be measuring it at a time when the household has a peak of activity or something, so there's a chance that you have more errors when you do it just once.
So there's this notion that you may not be capturing the average behavior. That sounds like what you're describing there. That is a factor. It's not the most. That is a factor. It's not the most critical one in the statistics sense, though, because the way we try to get around that is we hope that we measure enough of a sample, a large enough size, that if we do catch some households being having weird behavior, that we've captured enough that we don't have a lot of those. But it could happen. That is definitely something that could make them less good. Anything else? Any other guesses? Yeah.
So if there is any false reporting from the responder side, then if we have longitudinal data, then we can validate the previous observations.
We can. So we can use, and both of these are really good reasons why longitudinal data can be used and things you can do. So we've got this aberrant behavior we can check, and we've got this notion that we can kind of validate. But from a, yeah? So consistency, yes. So you're all thinking, and you're all thinking about the number of observations we have and the repeated, and they're all valid. But there's a couple more important things statistically that I want to cement for you. One of them, Okay, number one is that if you remember in models, what I said, one of the biggest threats to a good model is that we omit things that could influence the outcome. That we omit things. We could omit things we know, and we omit things we don't know that affect Y. What happens when we have a cross-section of data is that we don't know the bias that a household itself brings, if we're measuring households, to the context. We don't know how it's sort of like this aberrant behavior. We don't know if there's bias from the household itself. Let me give you an example. Let's say a household just wants, they have no concern for the environment wherever that's their ideology, and they hate public transport. They hate it. But we don't know anything, we haven't measured anything about how they feel about public transport, and all we do is observe that even though they have a bus right in front of the house, they never take it because they hate public transport. We don't know that about the household, and in a longitudinal study, if we measure them twice, we can factor, and I'll show you how we do this, we can factor for the fact that those households exhibit the same biased behavior across time. We can control for that. We can recognize it. But in a cross-section, we can't. Okay, there's one more really, really important thing, probably the most important. In models, what we try to do is say, when we get down and start to get in the models, we start to say, so if I changed X by some amount, it would change Y by some amount, right? So let's say, so if a household had 10,000 Australian dollar more income, they would be more likely to drive a car, right? Something like that. Wait a minute, if you think about that, that implies a before-after interpretation. If a household's here, and I come in and give them more money, so if now they're here and I come in and give them more money, then afterwards, they would do something differently. But with cross-section data, you never observed an afterwards. You never, ever observed that. You only observed them once. So we never observed any household getting more money, more income, and changing their behavior. What we observed was fundamentally different. What we observed was a household over here with this much money, and a household that looks a lot like it with a little more money, and decide and use that information to look at the difference in travel to predict how much more they would travel based in the differences across households. But guess what? We don't know all those unmeasured factors that also describe the differences in those households. That comes back to the longitudinal. We can't control for that. So all we can conclude is the difference in the income of those two households is what explains the difference in their travel in our interpretation of the model. And it's incorrect. It's technically incorrect. We never observed the before-after. So, but we use models to do that. We say, well, if we change X here, this will happen to Y. Well, wait a minute. We never observed that ever in our data. So that's why cross-sectional data are more limited than all of these other types, where we can observe changes over time. So, in the study that I've looked at in Brisbane, we've been focused on movers, and people that moved location from one type of house to another house in a very different kind of urban context to see the impact on travel. And guess what? It's very different than, the changes in travel are very different than the differences that we observe across the cross-section. And I'll get in a little more into that study later as we get a little more tools and a little more depth. So it's different. You get more, richer information from these kinds of studies. And it's important to understand that. Okay? So the research hypothesis is the absolute cornerstone of the scientific method. So we use the hypothesis to say that we're testing things. We try to design experiments to do that. And it's about a relationship between two or more variables. We actually say that as a good scientist, what we are doing is failing to get information to reject a hypothesis. So we're trying to see if the evidence we have is consistent with our hypothesis or is sufficient to reject it. So I encourage you all to avoid things like, therefore, I prove this to be true, or I prove this relationship to exist. We actually don't. We just fail to get evidence to prove that it's false. So we say, well, I can't knock it off the pedestal, therefore I'll accept it. Right? And that's what we're doing as scientists. We're saying this is the best explanation of what's going on underneath that I can come up with, because I can't reject it. I don't have any evidence to suggest that this model of reality is wrong. So, we've seen that playing out with Einstein, one of the smartest man who ever lived, as far as we all know. He came up with a theory of relativity and special relativity, and doing science just like we've done. And so people have come along and refined his theories and found little tweaks in it and said, well, he didn't quite get this right and didn't quite get that right. Does it mean he was wrong? No, it doesn't. It means they've refined his articulation of reality a little bit better in a few places. And that's what science is. But he was a genius. But what he came up with was not that this is true about the world. Relatively, he's just said, this is the best model we currently have, and nothing can disprove it. And that's what we do with our modeling and our science. I did that before. So we don't confirm things. We don't actually confirm hypotheses. We just fail to reject them. But we often lose in journals and papers. We forget the terminology, the correct terminology. And the reason I'm emphasizing it is just to make sure you understand the philosophy behind the science. Okay. So we've talked about this. We've talked about longitudinal, before, after, cross-sectional. And those are really important to recognize. And as Sudeshna rightly pointed out earlier, it usually gets more expensive to collect things multiple times on road segments or households or whatever else. So you have to have a good reason to want to do it. And usually you want to answer some really, really complex, good questions to justify going beyond a cross-sectional study. But we do that. And then the before-after is a very special case where we come in with an intervention. And I imagine a number of you, if you're doing safety studies, you might be looking at those kinds of data sets where we go in and purposely change something and then look at the situation afterwards. So these things on the bottom, the taxonomy of degrees of control, these are things that we actually are able to do when we design the experiments and change values of parameters, go in and make an adjustment to a site, and then remeasure things. And so, again, as we go through and look at our data for the study or for this class, we'll see that they'll have arisen under any number of these kinds of designs, where things were manipulated or not, or chosen or not, depending on the nature of the study. So that doesn't work from over there. Okay, so I've already kind of talked through longitudinal studies. You've got these in your notes. So I talked through these in detail, so I'm not going to go through it again. The before-after study. Ezra Howard made this very, very popular and made this a very robust process in the road safety space. Has a fantastic book written on before-after studies in road safety. Really, really good book. I highly suggest reading that book if you are interested at all in the safety domain. It's a fantastic book, and he is an amazing researcher and thinker as well. If anyone ever gets a chance to meet Ezra Hauer, he may not be around in the profession for long. He's sort of in that semi-retirement mode now, but he's quite an extraordinary person. And then the cross-sectional, which we talked about. So cross-sectional studies are much more limited, but we probably make up the bulk of what we do. So the bulk of studies we do use the most limited type of data that we have. And so how many people here are working currently with the data set in their everyday work? And keep your, so quite a few, and how many of those, keep your hand up, are cross-sectional? Yeah. Yeah, I'm not going to ask, I won't call anyone. So almost everyone that had their hand up stays cross-sectional. The bulk of what we do are cross-sectional data set. And it doesn't mean we're not useful. They are useful, but we have to recognize the limitations. And so we'll talk about that as we start to look at the data and some of the models. So as you know, so manipulation, inclusion, we often manipulate variables. And we'll talk about more as we get into some of the experiment. Maybe we'll talk about it a little bit now, but why do you think we would want to manipulate values of variables? Why would we want to manipulate things? The values of certain things we see. Or eliminate or include specific things. Anyone have any idea in terms of our research design?
Please try to respond whatever
Okay.
you think, it's very more interesting.
So to replicate what we see in the real life, and if our model is, if our data is not actually representing the same thing, then we try to remove some of the bad data which we feel.
So absolutely right. So one of the things that we want to get, so usually we're talking about the x's, the right-hand side, what we're trying to manipulate or control, because the y's we don't control, right? We want to control the x's, but we want to get the range, the actual range that we see in the population. So there's a very important, another one of those nuggets of understanding that is really important, and I'll come back to this, but I'm going to say it now so you plant the seeds. When we have purely observational data, where almost nothing is a manipulation, let's say I go back to going into your households and asking questions about how you traveled. I can't manipulate anything. I can't assign your household an income level. I can't drop off cars at your doors I mean, I could, it'd be a very expensive study, but typically it can't because it's too expensive, too prohibitive. So I can't manipulate your access to a car, your household incomes, and those sorts of things. So they're all as observed, right? There is an extreme limitation to that. It would be much better if I could manipulate all of those things in your households. If I could come in and give you more money or less money. You wouldn't be very popular getting on the less money, would it? Or I could give you cars or take away your cars. If I could control that environment and then observe your behavior, it would be a much better study. You would all hate it, right? It'd be very difficult to do, but just conceptually, much stronger. Why? I want to become clear to you why that's the case. Why is it better that I could control the variables in your household rather than just observe all of the variables and do a study based on what I observe? Anyone have a clue?
You're ultimately trying to measure the behavior of the person, and when you start removing variables, then essentially
Yes, you are correct that we're trying to get at the change of variables, but let me be more articulate about. I wouldn't observe a change. So if what I'm describing is if I went in and just adjusted all the households to all of your attributes, your cars, your things, and then I go in and measure you. So there's no change. Your household car ownership and moped ownership and bicycle ownership is something I've controlled rather than just what you already have. So there wouldn't be a change. It's a very tough question, and but we are going to get to change. We're going to try to measure that, it's a very tough question. I've asked a tough question. I'm setting you up a little bit, so I don't want to do that. I'm not trying to do that. So,
what I think is, like, suppose we are observing we're trying to capture some data. We have a decidable given. We want a goal that we want to reach. So if we can control the variables, if we can manipulate it, then maybe we can design a system to reach that particular goal and understand properly what is the influence of a particular variable or a factor. Like, for example, if it's like, if, as you said, we can change, we can put a car or we can take away the car, then if we can observe or we can monitor that behavior, we'll understand what is the effect that a car ownership can have on our system. And if we can understand and we can see, okay, we gave so many households, so many cars, and then we get equilibrium.
Yeah. So you're both right, and I'm going to take what you've said and I'm going to articulate it a little bit differently. But the reason is observational studies are problematic is because it's going to be difficult for me to find people, households, that live fairly far out that don't have cars, if I just look at the observational studies. It's going to be difficult for me to find households in the wealthier kind of land use, but that actually don't have the wealth that goes with it. It's going to be hard for me to find people that live really close to their destinations, perhaps that don't have bicycles. So what happens in observational study is that we can't test, we can't understand the effect of the variables. We might want to know how someone would travel that lived in a high-income household that didn't have a car. But we don't get to find them because the high-income households do have a car. So we don't get to understand the effect of the variables as well because we don't get to observe the combinations of all those variables that we would want if we designed it. So this is capturing a little bit of both of what you said. And in an observational study, we're just stuck with what people have. And it may not be enough and configured in such a way that it enables us to learn exactly what we'd like to learn if we controlled those variables. And it is problematic for us in our models. So we'll come back to that. So we've learned about a bunch of things that are problematic for us. And purely observational studies are also problematic because we don't get to control and learn exactly what we'd like to learn, and we wouldn't construct it. So the classic problem of this in Western cultures is the car ownership and income problem. It's really hard to look at households in the high income categories that don't have cars. But we'd love to know how they travel without cars, if they had a lot of income. We don't, households that live in what we call accessible neighborhoods with access to public transport and bicycles and stuff, they also tend to own cars. It'd be nice to see what would happen if they didn't own cars. Would they use the infrastructure more? Would they do things? And so that's why the observational studies are really limiting in many cases. Okay, so I'm going to go through this part fairly quickly. We're coming up on our hour, and an hour is about as much as we can all handle. We need a little bit of a break and come back. So a lot of textbooks, depending on what textbook you see and use, they use the different terminologies for the same things. And so all this table does is really kind of show you what all you might see in the textbook. So when I refer to an outcome variable or the y or left hand, you could also see it as these other names. Okay? Response variable, signal dependent variable, outcome variable. And so I want you just, the purpose of this is to recall for perhaps from textbooks you've seen or notes you've seen so that you can put them in the context of how I use them in this class. In experimental design textbooks, they use the word treatment a lot. And they use omega factor, primary factor, dose, prime factor of interest. These are all the synonyms for an X variable that is something we've manipulated to try to understand the effect of it. And that's the same here. The measured factors are the independent variables, exogenous variables. Okay, another concept I'm just going to float to you now, and we'll come back to it, but very just conceptually. There's two terms. There's a lot of terms that we're going to learn that you may not have heard before, but one that's very, very important to understand. And it's the word exogenous and endogenous. Okay? Exogenous means from without or from the outside. Endogenous means from within or from the inside. And so exogenous variables are variables that are measured external to the model. And when you say outside, we're saying outside of the model. And I will get more specific about that later, but I just want you to understand exogenous is from the outside, endogenous is from within, and it is a very important concept to understand in econometrics, and we'll get more on that later. Just to cement that idea just a tiny bit, the left-hand side, y, is endogenous. Okay? All the x's are exogenous. We refer to them. So y is endogenous because it depends on the x's. Right? So it depends on things within the model. The x's are exogenous because they depend on things outside of the model. So they don't depend, their values do not depend on anything within the model. So y is endogenous, x's are exogenous. We'll come back to that. Because that's not always true. And it's a problem when it's not true. And that's one of those areas that a lot of people get hung up on. So then we have unmeasured factors. So we have all these measured things, and we have unmeasured things that we omitted variables, nuisance factors, noise, measurement errors, confounding variables, etc. Yes?
Sir, in case if two axes are not independent to each other, both that variables, the right hand side will be called exogenous or endogenous?
So independence is okay. Dependence is okay. So if the dependence is a covariation, so if things just happen to covary, two x's, that's okay. But if one of the x's is the determines the values of one of the other x's, that's not okay. So and there's a fine line. There's a fine line there, and it's a tough one, but we'll spend more time on that. But generally, we often get things that covary, that we don't think are dependent, where one determines the other completely, or even in some stochastic fashion. But they cannot be one x determines the value of another x. And when that happens 100%, we actually models won't work, won't converge. But it's more of a conceptual problem that we'll spend a bit of time talking about it because it's very important, and it fouls up a lot of research, that concept, far more than most people realize. But we'll learn it, and we'll get that. We'll talk about that one a bit. But it's a key question. Yes?
What is the difference between endogenous variable and dependent variable? Is there any difference?
So not the way we're going to use it. No, the dependent variable is endogenous. So the dependent variable is used to describe the y, the AY that we're interested in, or the outcome variable, and endogeneity is used to describe what factors influence it. And the assumption is that the outcome variable y is endogenous. It's also the assumption is all the x's are exogenous. And so the real problem happens, and as we'll see, is that when some of the right-hand side are endogenous. And that's where we run into trouble. But don't worry, we're going to come back to that, and we'll spend more time on it. So as I said in the beginning, what we're trying to do, and I hope you've written down in your notes some key things. I'm just trying to plant seeds now so that we'll come back to them later, and you'll go, oh yeah, Simon mentioned that on the first day, and that's what he was talking about. So I'm going to repeat and come back and get more depth in all of these concepts. All right, I'm going to talk about scale. We've just got a few more slides here. We'll be finishing up. There are 4 scales of variable measurement. Okay, their first scale is a nominal scale variable. Nominal scale variable has the least amount of information a variable can possibly have. It doesn't mean it's not useful. Nominal scale variables are really useful. But in terms of something having information content, a nominal scale variable has the least. And examples of nominal scale variables are these: name, gender, occupation. So they're usually categories. What you notice is that the categories don't have any ordering. They're just what kind of crash: rear end crash, rollover crash, angle crash, etc. There's no ordering of those crashes. They're just types. The second category of variables are ordinal. So they're like nominal scale variables, but these have order. And often these come from surveys. And we've all participated in surveys where people ask questions. How do you feel about this from a scale of 1 to 5, or 1 to 7, or 1 to 10? And we give ratings, right? And crash severity is another example. Property damage only crashes, minor injury crashes, major injury crashes, incapacitating injury crashes, and fatal crashes. So there's an ordering, and there are categories. The thing to note about these kinds of variables is that the ordering, the intervals are not fixed. So what you might respond to in saying you fully agree with a statement, and let's say that we say agree, partially agree. So some of those surveys just say partially agree and fully agree. So the interval that for you to go from partially agree to fully agree, that little point at which you go from one to the other, may not be the same as yours, or yours, or anyone's. They're all different. So there's no absolute interval at which one goes over the other. So we just know there's order, but that's it. Okay? And then what we have are interval scale variables, which we almost never see, but I'm putting up there for completeness. But they're interesting, and when we do see them, they cause some problems. So, question. Is 50 degrees centigrade twice as hot as 25 degrees centigrade? No, it's not. It's not twice as hot.
It depends if we take 0 as the reference.
What's that?
It depends if we take 0 as the reference.
Well, that's right. It does. It is not true. You have to have a 0 reference for that to be true. And the only temperature scale that has 0 is Kelvin. So, so interval scale variables are continuous, measured variables, but they don't have an absolute 0, and there are actually not that many of them. So the top category are the Kelvin scales, or something we measure with absolute precision and has the most information. It's numerical, temperature in Kelvin, height, number of cars in the queue, length of, number of pavement, the miles of pavement with rutting, etc. There's all kinds of ways we can measure these sorts of things. Okay, so they increasing information from nominal all the way up. And the reason I go over these is because in all of the data sets that we're going to use in the class, they're going to be full of a range of these. They're going to have all of them. Nominal, ordinal, and ratio. And we treat them differently in models. We have to recognize how they're measured, and because of how they're measured, we have to treat them differently in models because they aren't the same. And so this is a reminder for us that when we get the data and the variables and the models, we have to understand how these things are measured to treat them properly. And you'd be amazed that still people that don't have good modeling backgrounds can treat variables the wrong way in models. And it's absolutely useless and garbage. It makes no sense whatsoever. Okay. All right, last section in this. We're going to have some really weird things that happen with variables, too. And when these weird things happen, what we call anomalies, we have to know what they are, and then we have to deal with them the right way and econometrically. We have to recognize that something's strange, and we have to deal with it. So there are a number of anomalies, and I'll just talk about a few of them that are the more common ones. Measurement error is one of them. And when we know something's been measured with error, we often and oftentimes don't deal with it, but there are ways to deal with some measurement error problems. Another common one. This one throws a lot of people. And if you have questions that pop up in your mind with this one, you're not alone. A lot of people struggle with this one, and we will be dealing with it in the class. Unobserved or latent variables is something that some people have trouble grasping. And the notion here is that there are some things as researchers that we want to know, but we actually cannot directly measure. Therefore, we call it latent. Education, intelligence, attitudes towards transit. And really the idea here, the way to simply grasp this is that if we wanted to measure education, it's not just one thing that I would measure about you. If I wanted to measure our education level, it would take more than, for example, let me turn it over. If I wanted to measure education, your level of education, how would I do that? What's the one thing I could measure that would tell me your education level? You see the problem? There is not just one thing I could measure that would tell your education. And if that's the only question you need to answer, is there one thing you could measure to get at education? And if the answer is no, then education itself is latent. It would, for example, how many books have you read in the last year? Might be a pretty good predictor and measure of your level of education, as well as how many years you spent in university. But let me ask you this. You guys sit here and, a lot of you, in IIT, Kharagpur. Are there other people that we could invite to the room that might have spent as many years in university that you would argue is not the same level of education as sitting for 2 years or 3 years in IIT? I know that's the case in Australia. I know that's the case in the US. 5 years of college education is not the same everywhere. So it's not just measuring the number of years of education. So it gets complicated. So education is latent. And there are a lot of variables like that we have. And the basic rule is we'd probably measure lots of things in an attempt to measure the underlying construct of education with the same. Intelligence is exactly the same. So all of these latent. So we have censored variables as well. Censored variables are variables that can only be observed at a maximum value, and so show up in a database as a maximum value, and we often don't see beyond a value. Here are some examples. So my partner, who's actually also here, she went to Jaipur. So she's in Jaipur now for 3 days, and then she's going to join us here. She works in public transport, and she does a lot of public transport management. And I've asked her many times. She's looking at the efficiency of a lot of bus routes. I ask her, how many people are waiting at the curb on the buses that can't get on the buses because they're full? And she says, we don't know that. We don't know that. We don't have that information. It turns out most bus transit agencies around the world don't have that information. It's really, really hard to get. The only way you could get is to have a camera outside where the buses load and then have some kind of process that counts up the people that are waiting outside that can't get on a bus when it stops. So what we do often get is the occupancy on the bus. So that's a censored variable. If we had those occupancies on the buses, we would get the bus capacity only. That's the most we would get. If I was trying to estimate demand for buses, what's the problem with that variable? You see the problem? You can't answer that question at all very well with that data because they're censored at this thing. Well, if you recognize they're censored, you actually can start to get at that kind of thing. And the way the censored variables is that all of those things past the bus or stadium capacity would show up as extra observations at the limit. And if you recognize that, if we tell the statistics and the models that we have this situation, then we can reallocate smartly those censored observations into those last categories to try to do an account for that. But we have to be smart and know it's censored to begin with, and deal with it the right way. We have a similar problem with truncated variables where the instrument doesn't measure beyond a certain point, but we won't talk about that. So the key question, and this is one that we all get, and this is one I think we finish on here, is causality. All right? We all struggle with it. When does X cause Y? It's a tough one, and what I would suggest is that the safe thing to do is to never use the word cause, except in very extreme cases. If we just say that Y is associated with changes in X, and a 1 unit change in X creates a such and such unit change in Y, those are all comments that don't reflect causality or make statements about X causing Y. The reality is that we believe that you have to have a number of conditions to establish causality. And these are the ones that we would want to have to be able to say X causes Y. And the first one is one I always ask students or researchers, my own staff, regardless of the causality question, I always say, what is the material explanation between X and Y here? And it's a really good question. And actually, that comes from Ezra Howard. He was always big on this material explanation. You should be able to, as a researcher, come up with a plausible explanation for every single X in your model. How is this X influence the outcome? If you can't do that, we can't just say X is significant. That's my argument. It's significant in influencing Y. But if you can't explain why, what mechanism is that relationship, underlying that relationship, then you probably ought to take X out. If you can't explain why, and you can't address number one. And why would I make such a statement? Why would I stand up here and say, statistically something could be highly significant, some X in a model, and if you can't, I'm suggesting that if you can't explain why it is related to what the outcome variable, that you should take it out of the model. Well, on what basis would I ever make such a claim? Anyone have any idea? It's a tough question. Very good. Thank you very much. When we're researchers, we're testing hypotheses all the time. And we have a risk of being wrong. Right? We're always accepting a small amount of risk, usually about a 5% risk of being wrong. And if we do lots of models and lots of things along the time, we're going to make mistakes. And we're going to say something significant by mistake when it's not. And it's a random chance. And the way to weed out, to help us weed out those random chance, those coincidental cases where something is significant as Y, is to ask that first question. What possibly is the relationship between X and Y? If I can't come up, probably boot it out. Okay? But all of these are required to establish causality. Consistency. So if you find it in your model, then I should be able to find it in mine, and you should find it in yours. And we should start to see that same X show up multiple times, and everyone seems to be agreeing that there's a consistency of this effect, and that so we start to believe that it's true. Dose response, usually the more of X, then the more of Y. So there should be, you use certain values of X, I use different, and therefore, and they all seem to show different impacts on Y. We should be able to do it under experimental conditions. And the temporal chain has to be in place. This is that question about not the cross-sectional data, but we should be able to go, well, if it's true that X causes Y, we should be able to go in and change the value of X and observe a change in Y temporally. X first, and then Y happens, and all of those have to be satisfied for us to start to make claims of causality. Okay? We're going to be talking about some samples and your samples, and we have to understand about selection bias. We'll have to be looking at that carefully. We'll talk about that a little bit later. That's the foundation. That's the biggest, that's the only lecture we'll have on this big picture stuff. And we won't get to talk about a lot of it, but we will, as we get some data sets, go into some of these concepts. And we get into the model, we'll get into more of these concepts, endogeneity, exogeneity, latent variables, all those sorts of things. We'll start to get into them. So before I wrap up, any questions from any of you about what we just covered and yet you'd like to ask?
So, the before and after studies, so if you want to actually get a impact of certain intervention, for example, like we are implementing a BRT in a particular city, and we want to actually study how much actually impact it would have on the mode shares.
Yep.
So like public transport mode shares.
Yep.
So like we have collected the before and the data, and after the intervention we have collected the data. and we actually observed that there is a 20% improvement in the public transport,
Wow.
for example.
Wow.
So, but it might not be exactly due to only the intervention, and it might be actually associated with a lot of other things which are actually not in the purview of this study. Like
Yes.
it might actually be caused because of the parking pricing rising,
Yeah.
and like there might be many parameters like petrol price rising, so and more number of buses other than the VRT. So how do we deal with these kind of situations where there are many unknown
Yes.
variables?
Yeah. So let me repeat your question because so I'll make sure I understand it, but also describe what you describe is a problem with studies and something that vexes all of us in that context. So the question is, in a before-after study, in this case, where you might be looking at a specific intervention that you'd think would have an impact or designed to have an impact on mode share of public transport. But yet, from the before to the after period, not only do you have the intervention in the middle, but you had other things going on as well that could also influence mode share. And so how do you separate the effect of those other things? So there's two answers. One of the best things about what we're going to do in this class is that we're going to have multivariate models. And so it's perfect leading because I wanted to say this anyway. One of the most amazing things about the statistics and the models that we're looking at is that we have the ability to look at a number of things influencing something all at the same time. So we have the tool set to look at the intervention as well as the road pricing, as the fuel prices and other things like that. So we have the tool set to do it. So that's really, really important. The problem is that the context you're working is in that observational study space. And as I mentioned earlier, the problem in the observational study space is that we can't control a lot of things, and so we end up at the end of the day having things vary together, and it's hard to separate out the effect of that. The way we would normally do that is in the design, is to set up a control in a before-after sense that would have been somewhere that had almost all the effects of everything else, but not your intervention. So you would try to observe somewhere else, say in the region that didn't have the intervention, but did have the fuel pricing, and did have all those other things happen, and look at the change there, before to after, as a way to gauge what was the effect of all that other stuff. And then that should be your good estimate of what happened there. And then over here in this sample, you have the intervention as well. So the only difference between these two groups, theoretically, would be the intervention. So that you could then isolate the effect of the intervention. And that's actually out of Ezra Hauer's before-after design book. He describes that kind of approach in a safety context, but it's no different. It's the same thing. So you use a treatment or comparison sites. You can use more than one. You can use several comparison sites to measure the effect of all those other things. The problem, but the logistics, it depends. How widespread was your treatment, and do you have comparable sites, and all those things. And so they're not trivial questions, but those are the two ways to generally deal with that. Okay. And, yes.
Yeah, so as he said that it is described quite well in that observational before-after study by Ezra Howard, but mainly in the area of safety. So basically it is, naive before-after study when you really do not take any control site, and then as he mentioned that if a very similar situation can be found elsewhere, so that you take as control. Let's say you are studying city of Hyderabad and city of, let's say, Indore. Both has BRT, but then the petrol price probably did not change at a point, and then now petrol price is increasing, and how the ridership is also increasing in two cities. These are some of the ways you can with control side to take the effects of those out. So that group, as he mentioned, is very good for this type of stuff.
Okay, and any other questions before we break? Yep.
How do you decide on how complex your model should be? So if a very simple model can explain what you're trying to do, but making it more and more complex gives you a little more percentage of better predictability. When do you decide that, okay, this much is too much, or when do you stop?
Yeah. Well, so and that is a key question. It's again the question of how much complexity. So we will dive into and show you. So a lot of the methods we look at will have what we call a penalized measure of fit, and so we will get a goodness of fit measure, but we'll penalize it if the model is more complex, so that we can make comparisons to see if that measure got better with the additional complexity. But in addition to that statistical test, it's really a question about. So some of that is usually answered by, well, how much more explanatory ability do you get by adding that complexity? And also, is it complexity that no one else has looked at or pondered before? So that might be something that would compel you to say, this complexity that I'm talking about here is something we don't know about right now. And that's why I'm going to focus on it, because it's new. It's new knowledge. And it may only add a little bit of explanatory power, but it is explanatory power, and it is something about the process that we didn't know before. So that might encourage you to want to have that. But if it's not that interesting, and it's not that insightful, and it's not adding much, probably would want it. So it's subjective. And as researchers, we have to make those subjective calls. But those are some of the factors you'd consider. It's a great question. That is one of the biggest questions that we ask. But we'll look at some measures. So we'll come back to that and deal with it. Any other questions? Yeah.
Is there any systematic method to determine the minimum sample size of a model?
Fantastic question, and I'm going to give you a short answer now. I'm going to give you a long answer because later. I'll give you a long answer later because that question is one of the most misunderstood questions in, I think, in modeling, even by people that should know better. But the short answer to that, so the question is, how big should the sample size be in my study? And how do I know that? And if you ask around, you'll get a whole bunch of different answers. And I contend that it's because people don't know and haven't studied the sample sizing literature, which is actually quite hard to find. But there are a few good books about it. But the fundamental question is this. What do you want to test, and how sensitive do you want your test to be? That's what determines your sample size, nothing else. Nothing else. So there's a question of representativeness in the sample. If you're sampling geographically, what regions do you want, how much representation? But once you've answered that question, the question is, let me make it in concrete terms. Let's say you were studying mode choice, and you wanted to know the effect of income. Your primary question was effective household income on mode choice. You would, to determine sample size, you'd have to answer the kind of question as, well, okay, how sensitive do you want your model to be? Do you want your model to be able to pick up a shift in mode choice from 1,000 Australian dollar increment in household income? Would you want to be able to detect that difference? You say, well, no, that's a very small difference. No, I don't know. Okay, well, 5,000 or $10,000 or $20,000, that number that you pick for the X that you want the model to be able to pick up the sensitivity and the change in Y is the number that would determine the sample you need. And so you back calculate from, you say, okay, yep, I absolutely have to be able to detect a $5,000 change in households. I want to know when that happens. I want to know the effect on mode shift, and I back calculate there. Then that implies a standard error of the effect of income on that, on mode share, and from the standard error I can then standard error has n in it, and so then I back calculate. So And there are software programs that can back calculate for you and sample sizes based on those kinds of things. But that's the answer. It's how sensitive do you want it to be to some change in X? And there is no other, statistically from sample size, no other question that answers that, that can answer that for you. That is the way you get to the answer. And other than the representativeness question I said. So, but it's a great question, and it throws a lot of people. Yes.
But Simon, sometimes like even when we did the work related to the Bayesian,
Yes.
sometimes we assume that if we have very large sample, it asymptotically behave as a normal, and then many assumptions we do then are tend to be valid if we just took very small sample.
Yep.
So yeah, what you explained to us just now is a very important and philosophical thing that I think not many books also explain that. Yeah.
No, they don't. Many books do not talk about it. My book doesn't talk about it. A lot of books don't talk about how to do sample size because it's an experimental design consideration. But the question that you asked is one that, so many forums say, well, what sample size do you need? And any answer that says, oh, well, you need such and such, but they don't say, well, we calculated that by what was driven by our research question, then it's just a ballpark. 30 is the number you normally need to get asymptotic properties for normality, and 30 is a very small number, so we almost always have more than 30. But it's driven by the question that you're asking and the sensitivity. It's really about sensitivity of the model. How sensitive do you want it to be? And so, yeah, that's what drives. Okay, yes? Yeah, so we've got the last question here. Yeah, good point.
So you said that for a cross-sectional data, when you make a model, and then you try to infer from the model. For example, you said that if the income changes from this to this, the likelihood of owning a car would change from this to this.
Yes.
But that is not an observed thing. So this is the limitation of cross-sectional model. So unless we don't validate that model from some entirely different data set, is it wrong to make any judgment from that model? So unless we don't validate a cross-sectional data model, would it be entirely wrong to make any inferences from that model?
So no, it's not entirely wrong. So it's a great question. So when you make an inference from a cross-sectional model, when you're saying if you change this, then this would happen, is it wrong? No, it's not wrong. But we always have to be our own worst critic and the person that is aware of the limitations. And where it creeps up is that there's the real problem. Let me see if I can explain the problem to you that will happen. I'll use that exact example. You have a cross-sectional data and you assume that you change income again, and it changes the mode, let's say mode share. The problem is that income is also associated with car ownership, and it's also associated with where you live. So it influences probably distance of travel and other things like that. So that shift in mode could have been more to do with a distance effect or a car ownership effect rather than income. But because you can't separate those two in the before-after case, and you didn't observe it, we'll assume that the estimated effect is because of that income. But it could be those other things. And we don't know because we have cross-sectional data. And we didn't observe before-after. It's also the observational nature of the data. So it's problematic from that perspective. There are other cases where we have self-selection, and that I'll walk you through later in the class a self-selection problem that so interesting. I'll just show you I'll pull out a little bit to illustrate this. But the other thing that happens with the cross-sectional is we have a lot of self-selection that happens. So households that, let me give you an example. Households that move to areas with high accessibility for active travel are self-selected to those neighborhoods. That is, they prefer to live in that kind of neighborhood. So then we go do a study and says, oh, well, they live by, sidewalks and they ride their bike a lot. That's great. The neighborhood's influencing them. Well, no, wait, no. They actually were attracted to that neighborhood, self-selected to that neighborhood, and it's the quality, it's the unobserved factors of the household that make them walk more and ride more, not the neighborhood itself. And so, but you don't ever observe that. You couldn't in a cross-sectional study, so you have this pollution from a self-selection effect, which is also happens in this cross-sectional study, which is, when I discovered that was that panel data where we could observe changes. And I'll show you the results from that to show you how polluted they can be. But it's a great question. It's a tough one. But it does happen, and we have to just be careful. And it doesn't mean it's wrong, but we just have to know the potential limitations and think through what could be happening here that I need to possibly account for. Okay, so let's take it there. I love the questions. I do love the questions. Keep them coming. That's great. That's what it's all about. I hope you got something out of the very first discussion to set the scene, and we'll get into some more detail, and you will get into some modeling. So everyone have computers? How is that going to work? Yeah. Okay. Okay. Beautiful. Beautiful.
So we'll take a quick break. Tea is served outside, so you can always take out and have tea and biscuits.
Yes, biscuits. Okay.
And then you can come back. And thank you so much, Simon, for such a great
my pleasure.
start. I think all of you are now thinking about the modeling and the statistical model a little differently. Not the theoretical things, but also how it is applied. The philosophy of it has pieces and stuff. Okay, so, yeah, I think it is start with this side.
Okay, welcome back. I hope you. I'm on my second thing of tea, and I think it's going to be enough for me. A little bit of caffeine in this. A little bit. They're so small. There must be a lot of caffeine. There must be a lot of caffeine in these. Okay, so what we're going to do now is we're going to go through one more lecture, and this is going to get us to our first very simple modeling exercise. So I realize that probably not everyone brought their laptops today. So what we'll do is we'll group up, and so hopefully we'll get try to get 2 people per computer. Hopefully there's enough for that. There might be a case where you have 3 people around one computer or whatever, but we'll do a group exercise. But definitely tomorrow we'll want to get everyone on a computer if we can, so you can learn the software and get familiar with the software if you don't already know it. I tell you, it's really worth knowing, and not only to have knowledge when you come out of here, but have a skill set to be able to analyze data. So every time I run this course, students come out knowing how to run the software and estimate models, and it's really, really good. So it's a useful tool to have. It's good for your resume, but it's also great for your skill set. So, all right. So this lecture is a little still more in the building phase, but now we're going to be more in the details. We've given that one big overview lecture. Please ask me questions if you want to pull back out to the big picture. It's important to understand the big picture of what we're doing always. If we get too stuck in the weeds and the details, sometimes we lose track of what we're trying to do. So if you feel like you're getting stuck in the weeds and the details, ask me a question to pull me out and to remind everyone why we're doing what we're discussing, and ask questions as we go. I'm not going to spend a lot of time on the equations. I will talk about them. The book goes in great detail on the equations, and there's tons of books that talk about the equations, and I don't really want to spend our time there. So I'll do them as necessary, but I really want you to understand what we're trying to do, okay? And what I have found. After 20 plus years of teaching statistics and econometrics, is that the trouble is not in understanding the equations. Although there are some difficulties there, but the trouble is in the interpretation and understanding of what the equations mean and how to make sense of them. So that's why I'm going to focus on that. Okay? All right, so what I'm going to talk about here is a lot of what people outside this kind of room work on, and those are econometricians and statisticians. So they've done a lot of hard work for us to establish a set of principles that guide all the models that we'll be talking about in the class. And what I want you to understand from this lecture, what I want you to walk away with is the understanding of those principles or foundations of what we do in modeling, and why certain models we can rely on them doing certain things for us. So that's what I want you to get away, is what are the contexts in which all these models are going to be operating. Model estimation. Let's just start with and dive in and think about what a model is. So consider a model of household vehicle miles of travel. Household miles driven over some time period. Y. So we have our left-hand side. Y sub t is the dependent variable. And we have beta naught equals beta naught plus beta 1 x sub t plus epsilon. Now, I'm going to go slow here in the beginning, and we'll go faster later. All of our models are going to kind of look like this. But we've got, this is usually the intercept term, the estimated. This is usually the notation that you use for the unknown true parameter of the model is a capital beta, all right? Or the Greek beta. That's a Greek beta 1, x sub t, and epsilon sub t. Epsilon is the error. So we always use epsilon for the error term. It's important to know that in all of the theory that we do, underlying all of the models and all of the theory is this notion. And it's really critical to get this. If you get a few key principles, you'll understand all the technical stuff. It'll all make sense. If you don't get a few key principles, all the technical stuff is really confusing. Okay? One of the key principles is that the assumption, and remember in the first statement I said, statistics is a philosophy. It really is. And this is one of those things that I'm saying why it's a philosophy. The philosophy of statistics and statistical models is that there is some unknown underlying true model that exists that we will never know. And you have to understand that. And that we notate that model with these capital betas. Okay? The idea is that those betas are unknown constants. No variation whatsoever. Beta naught and beta 1 in this model are scalar values that we will never know. But we will know, we will know, we can measure the x's, the y's, and we don't know the epsilon term either. That's really critical because everything falls out of knowing that philosophy, and that's how we start. The reason is that what we want to know, let me go back real quick. What we actually want to know, and what we're going to spend a lot of time on, is, well, if we drew a sample and tried to estimate this model from a sample, knowing that we can't get this model, we'll have estimates of this and this. Those estimates will have variability, and we're going to be very interested in how those estimates of these true unknown parameters behave. And luckily, the statisticians and econometricians have done all the hard work, and they say, okay, well, this is, under certain conditions, they behave this way, and these are how we want them to behave, and when they behave this way, everything's good and great, and we can go ahead and proceed. So I'm going to talk a little bit about what they've done, And then we're going to go ahead and proceed and start to estimate models and not worry so much about how they behave. But it's important to understand what they've done. So there are a couple of properties that the statisticians will talk about. We'll talk about small sample properties, and they'll talk about asymptotic properties. So statisticians talk that, and the statistics are slightly different. We're not going to worry about it a whole lot other than what it means. But the small sample properties are that hold in small numbers and small samples in exact values. Asymptotic properties hold, and statisticians use phrases like, as the sample size approaches infinity, these things tend to do this. And so therefore they're okay. And as sample sizes get large. So let's talk about. So one of the things that we care about is on those small betas, when we estimate small betas for the large unknown betas, is bias. And bias is this notion that we want the expected value of our estimate. So this little caret, this little hat stands for the estimated value of beta. We want the estimate of beta to equal the true value of beta, the expected value. All right? So what is the expected value of the average? So what does that mean? That means if I collected samples over and over again, and each time I estimated a sample, I calculated a beta, that the average of those betas over all those samples I would collect would equal the true unknown parameter beta. That's all it means. Now, the weird bit is, we don't get to go and collect sample after sample after sample after sample. We usually collect one. So we rely on what statisticians have done to tell us how our sample will behave in the long run if we in repeated trials, even though we'll never do repeated trials. We only do it once. So it's important to know how our one draw is going to behave. And then we have small sample and asymptotic unbiased. And so this is just two different expressions saying two different things. One is talking about when you have a small sample, and one is the expression that says when we have very large samples. The concept is, though, that statisticians and we want our parameter estimate, our little beta, to be unbiased. Okay? And so what does that mean? Well, a bias is really that the true parameter is some distant away from the actual value. So underneath the value here would be the true value of beta, and the distributions are the uncertainty around our beta. Because if for each sample we'd get a different value of beta, estimate of beta, then it actually has a distribution. And what we want is that the distribution to include underneath it the big value of beta. So intuitively, what we want is the big value of beta to be right in the center, well, in that distribution. We actually don't know where in the distribution it is. And we want the distribution to be as small as possible. Right? Does that make intuitive sense? When we do the distribution or sampling distribution of our little beta, we want to be as tight as possible, because the tighter the possible, that means the true value of beta underneath it is in a smaller range of values. That is, we're more certain that it's between here and here. I'd much rather be able to stand in front of you and say, therefore, based on my value of beta, the true value of beta is between here and here, rather than me saying the true value of beta is between here and here. Intuition works really, really well. So that's what we do, and that's what statisticians do. So efficiency is another property that statisticians care about. Efficiency is a small sample property. You'll see in most of the models we do, we don't have small samples. Less than 30, often we don't have. So we will talk about another property called consistency, which is the same thing, same concept, but is in large samples. Now, one estimator is more efficient than another if it has a smaller variance. So as I just showed you, an estimator that would have give me a standard error of the estimate this is better than one that gives me one that's like this. Okay? And it turns out that there are different ways to estimate the true values of beta, and so we can choose. And we've all probably heard of ordinary least squares, maximum likelihood. There are other methods, but those are the ones that we will talk about and learn in this class. We call the best unbiased estimator is the most efficient among all unbiased estimators. So we want it to be unbiased, and we want it to be small. Those are actually the two basic concepts that econometricians and statisticians have done for us. If we understand those, we can develop a common language and talk about those fairly carefully, and we will talk about those throughout the course. So we want the titer of these two estimators rather than the top one rather than the bottom one. Okay, so how do we identify the best? Well, luckily, some really smart statisticians have come along, and there's this couple of them, Kramer and Rao, that came up with this theorem that says called the Kramer-Rao bound. So they developed this theory or a theorem that came up with a Kramer-Rao bound, and essentially it goes like this: if you can demonstrate that your estimator achieves the Kramer-Rao bound, you can do no better. So they basically came out with a limiting value for which there's no more, you can't do any better. Because before that, statisticians were competing about getting more efficient estimators. Well, I got a better one than you did over there. Oh, well, I came up with this new method and it's smaller than your, more efficient. So the Kramer-Rao said, wait a minute, all this fighting back and forth, let's figure out how do you know when you've achieved the best? There's no more fighting to be had. And that's what they did. And this is the Kramer-Rao bound. I'm not, it's some fancy equation that shows this is how you can get to the most efficient estimator. All we need to care about, really, is that the estimators we're using are the most efficient they can be. That is, they're efficient, and they're going to give us the most detailed inference about the x's we're talking about. Yep. Yes, L is the likelihood. Yep. So we will get to likelihood functions. We'll be looking at lots of likelihood functions. But because I haven't defined a likelihood function yet, but that's a good question. All right. So the statisticians have proven that for the estimators that we're looking at, and we're not going to spend a lot of time looking at that. But we'll talk through it. Again, it's conceptually what we want to know is what's happening here with these estimators. So consistency is what we will see more of than efficiency, because consistency is a large sample property. And typically, the models and that we are going to be using have been derived with large sample properties, which means that they may not work really well with small samples. And so we have to be careful with some of our models with small samples. So consistency is an asymptotic property. So as the sample size grows and grows, the models behave better and better. A consistent estimator has a distribution which collapses on the true parameter value as the sample size increases. Beta hat converges to beta in the probability limit for any probability. Oh, I don't know why it's doing that. Sorry about that. That was very strange. Okay, that's where we were. All right, so consistency is in the limit. You can see it as a limit as n approaches infinity. Then the difference between the estimator and the actual value approaches 0, right? Which is what we want. And you can see that in this graph here, that the consistent estimators can be biased and efficient. So what we'll talk about in some of the models that, and this tends to happen sometimes, we can trade off one of those properties for another. So we're willing sometimes to sacrifice bias, so get an unbiased estimator if it's more efficient. So efficiency is really, efficiency is the ability to make inference, right? So efficiency is where we do the hypothesis testing. We want to rule out 0, usually 0 as the value of one of our x's. And the efficiency is what directly influences that hypothesis. So we do want efficient estimators. Sometimes you have to make a trade-off. And there'll be a few models that we look at that we might have biased but efficient parameters. And so just recognize there are cases in some of the models, more complex models, where you might not have unbiased estimators, but you will have efficient ones. And that's what we're talking about. Okay, so that can happen. It's not desirable. We would love to always have efficient, unbiased estimators. Okay, other asymptotic properties that we will talk about is asymptotically normal. Okay, an estimator's distribution converges to a normal distribution. Now, why would we want that? Anyone guess why would we want something to converge to a normal distribution? Yeah, so when something converges to a known distribution, it doesn't actually have to be normal, but normal is a very nice one. Because then we can make inference. Unless you know what the distribution is, you can't start to talk about probability values. So we want to know how something's behaved. So you'll see in a lot of the models we have, the assumption is, and the statisticians have shown, that in the limit, even though something might not be normally distributed to begin with, the resampling of estimators end up to be approximately normal. The central limit theorem is a really, really amazing theorem that has shown that even in relatively small samples, things that actually behave quite erratically tend to start to look normal quite quickly. And that helps us. And so we'll look at this in a minute, and I'll show you how this all comes together. All right, so just big picture, just to review. I went very quickly through what statisticians and econometricians care about. In an econometrics class, you'd spend a lot of time on that. You'd do derivations and theorems, and that's not the focus of this class. But what the take-home messages are is really statisticians and econometricians, and we care about, are the properties of those estimators that we get from models. And we want them to be well behaved. We want them to be equal to the true unknown parameter that we think is responsible for generating the data in the real world. But because we don't know it, we draw a sample and we estimate it. We want it to be unbiased, and we want it to be efficient. All right, so now most of you have probably heard of, how many people have heard of ordinary least squares? And that's review. I just want to show of hands. I'm not going to ask anyone any questions other than, whenever I ask somebody to raise their hand, all I'm going to do is, I'm not going to then turn to you and go, okay, tell me what that is. I promise. I'm just going to ask so I know who's doing what. So again, show of hands, ordinary least squares, who's done it? All right, I'm going to go through, it looks like everyone pretty much has done it. I'm going to go through it fairly quickly because then we'll get to the It's the more interesting stuff, and we'll get to the software as well. So let me understand, how many people have used LIMDEP before? Okay, a lot smaller number of hands went up when I asked about that. So we'll spend some time getting up to speed with LIMDEP, and then again tomorrow we'll have to again because a lot of you won't be doing the typing today. Okay, so least squares estimation, as you remember, is one way for us to get estimators. And conceptually, if you think of a cloud of data and a straight line and a line going through it, we are minimizing the squared deviations across the entire sample to the line. Okay, and that's what that expression is. The difference in the y hat. So y hat is the equation of the line itself, and the yi are the observations themselves. That difference squared over all of the observation and minimized. And that gives us a line that minimizes the squared deviation, or ordinary least squares. It's called, the word ordinary comes from the fact that there's no weighting going on. That's all that ordinary means. And least squares is really what describes that function. The yi minus y hat is the residual. So the difference between the y, the line, and the observations is the residual, or that's where all that magical uncertainty sits. What we don't know about the process that's not being explained by the process or picked up by the model. It's easy. Now I want to point out to you, it's easy to visualize that in 2 dimensions. It's much harder in multiple dimensions. And so you have to think in your mind's eye that we have a multi-dimensional cloud of data, and we have a regression function or a model that goes in multiple dimensions trying to reach those data points. And so this difference between the fitted and the actual becomes much less easy to visualize in the multivariate model case. But the concept is exactly the same as the 2-dimensional case. The least squares regression, I'm going to give you an overview. That is, first we show, and we do it in the book, and almost all books do this, show you the simple algebra approach to linear regression, ordinary least squares. And then we quickly say, well, wait a minute, the simple linear algebra, but the simple algebra approach works very well when you have 1 or 2 variable x's. But as soon as you go to many, many x's, it becomes much more convenient to use matrix algebra, linear algebra. And so that's all I show here. I'll go through that very quickly. The important thing to note is that everything, all of the computer software packages, LIMDEP, all of them, even Excel, they use internally coded linear algebra functions to do all of the manipulation of matrices in them. Show of hands who've had linear algebra course in linear algebra. Okay. Okay. Yeah. Okay. So matrix algebra. Okay. So if you were doing a course in statistics or a degree in statistics or econometrics, you would probably end up having 3 or 4 linear algebra classes just on linear algebra. But so I'll go through that, but since I didn't see a lot of hands, I'll go through a little bit. But this is the simple algebra approach, that we have this minimization function, and we use simple algebra, and we can show that what we're really minimizing here is y on the bottom is yi minus beta naught minus beta 1 xi. That's the regression function with 2 slope intercepts, beta naught, and 1 x, right? Simple 1 predictor variable. We're minimizing that function. So we set the partial derivatives of q with respect to beta naught and beta 2 equal to 0. And then we end up getting a couple of equations. So we have two partial derivatives set to equal to 0, one with respect to beta naught, one with respect to beta 1. And if you solve those two equations and rearrange terms, you end up with a couple of new equations. They're minimum equations because the second derivatives are positive. And if you solve simultaneously, right, two equations, two unknowns, you get the simple algebra equations for beta naught and beta 1. So conceptually, big picture, so we're in the details and the weeds, big picture here is these are one of many potential mathematical formulas we could use to come up with estimates of beta 1 and beta naught. Estimates of true unknown scalars in the population, of a model that we think exists, but we've got one approach, ordinary least squares, that derives for us an estimate of those true unknown parameters. It turns out, and as I'll show you in a second, that statisticians early on, not anymore, this is old news, but 20 years ago, spent a lot of time looking at the properties of these ordinary least squares, estimates, efficiency, consistency, bias, to see if how well this mathematical routine or these estimators worked. You can, for the case y equals beta naught plus beta 1x, it can be shown that beta naught is equal to y minus beta hat x bar. Okay, and show you that. It turns out there's as I said, it gets much quicker or much simpler if we just use matrix algebra once we get more than one x. And everything, all the math becomes very, very simple. And it turns into that beta naught equals x prime, so x transpose x inverse times x transpose y. And that's in my book in the appendix, and it goes through in great detail. I'm not going to go through that with you, but these linear algebra is essentially taking vectors or matrices and defining a matrix with a term like x would be represent an entire matrix, and you're doing operations on matrices. And I certainly don't have enough time to teach or talk through the linear algebra, but it's if you wanted to go further into statistics and econometrics, it's worth doing. And I sat through a couple of those courses, and it's interesting, but the stuff we're going to talk about is much more interesting. And so we have vector of dependent variables. The prime indicates the transpose. The -1 indicates the inverted matrix. And if you take a course, you spend a lot of time inverting matrices, which is not that fun. So under very general assumptions, the Gauss-Markov theorem demonstrates the least squares estimators are blue. Okay? So Gauss-Markov, apparently if you're a statistician, you find somebody to work with and you come up with name theorems after two people. So Gauss-Markov, those two gentlemen worked together and showed that ordinary least squares have all the properties we want. And then the acronym is BLUE. So when we say BLUE, and I say BLUE in the class, it stands for Best Linear Unbiased Estimator. Okay? And so, fantastic. So all of that fanfare, all we're saying is that ordinary least squares is a way to get estimates of the true unknown parameters, and they have really good properties. Fantastic. The bad news is that ordinary least squares runs out and for being useful for us quite quickly. And so we have to go to a different technique of estimation. And I'll tell you why that is. But a lot of software packages for the basic stuff use ordinary least squares, and we use ordinary least squares often to get initial estimates in our models, and you'll see that when we go through. So, assumptions required to prove that something is blue: normality, zero mean, homoscedasticity, serial independence. All right, so we haven't talked about a couple of these terms, and we will now. Normality, we have talked about briefly, but normality means that a distribution converges to the normal distribution in the limit. Okay? And we can show that in the statisticians, again, that show that happens for certain distributions under certain circumstances. Luckily, all that's done for us. Okay? Zero mean means that that's the unbiasedness, so the expected value. Sorry, that's not unbiased. The zero mean is that the expected value of the error terms is zero. It is another way to express bias, but it means the average of the errors is zero. That's actually guaranteed in ordinary least squares estimation, but it's not guaranteed in other methods of estimation. Homoscedasticity, so that's the first time we've used that word. Homoscedasticity means that the variance is constant across all of the x's. Okay, the variance, that is conceptually it's the scatter of the points around the fitted line, is about the same amount of scatter everywhere across the line. It doesn't get smaller or it doesn't get larger, and if it does, we call that heteroscedasticity. So that's an assumption that we need to have in order to have best linear unbiased estimators. The last one is serial independence, and that is actually there might be a couple more, but so the serial independence, so that means that the disturbance terms are not correlated with each other. So that can happen if we have observations over time, quite a bit. So something that happens in time period 1 often is related to time period 2. And so that we call that lag dependence. And so often, if we have a model of that, we have correlated disturbance terms. But we can't have that in order to have best linear unbiased estimators. So the last one we have is non-stochastic X. It is not random and has fixed values and repeated samples. That is a fancy way of saying endogeneity. So that last A5 is a violation of endogeneity. We can't have variables on the right-hand side that are endogenous. And so that means it's not random. It means it's actually a function of one of the other x's or of y. Okay. So, as I said, ordinary least squares, if some of you, and this is probably a review for many of you and brand new for some of you. So, ordinary least squares doesn't always work really, really well for us. Because there are models that we're going to look at. Most of the models we look at are sufficiently complex that we need to go to a different estimation technique. Almost always it's maximum likelihood. At the very end of the course, we'll talk about a whole new estimation technique just to throw everything wide open. We'll talk about Bayesian models, Markov chain Monte Carlo models, which is a completely different estimation philosophy, and everything's different. But most of everything we talk about are what we would call classical models, and they are going to use maximum likelihood estimation. And I'm going to walk you through this, and my goal is, by the end of this session, you will conceptually know very, very well the difference between maximum likelihood and ordinary least squares. Yes? Yeah. Yeah.
Yeah. So, is it also like, because what it is meant
So it could be fixed values could be fixed against or multiplicative of another, say another value, or another x. I mean, if we had a truly non-stochastic an x that had no variation in it whatsoever, it wouldn't violate this. So that would just mean that that x would not be significant in the model, right? Yeah. But a non-significant x wouldn't violate the properties for blue, but an endogenous x would. Okay, so the principle of maximum, yes.
Is it like if in a matrix algebra, if we do the ordinary least square method, then the estimator would have all the 5 properties, or is it the other way around?
So what it's saying here is that, what we're saying here is that, let me go up. So I'll repeat the question. So the question is, well, let me just give the answer and see if that clarifies. I think it'd be easier. So what I think the question is, what is this saying exactly? And what it's saying is that for ordinary least squares estimates to be blue, these conditions have to hold. If these conditions do not hold, then ordinary least squares estimates are not blue, are not assured to be blue. That's what this is saying. All right. Okay, so I need 4 volunteers. How about you 4 to come up here with me for a second? I want to illustrate, we'll come over here, illustrate exactly the difference between ordinary least squares estimation and maximum likelihood. So let's all stand in a line here for a second. Now, I did a good job. And you're all doing a good job too. So what I wanted to see is that there's difference in heights of us, right? There is a true unknown height. There's a true value of our average heights, right? There's a true unknown value. We don't know what it is. We have, and maybe it's the height of people in this room. We have a sample we've drawn up here, 5 of us. And the ordinary least squares, I want you to visualize the difference between ordinary least squares and maximum likelihood. Okay, so what we just went through is ordinary least squares. What ordinary least squares would do is imagine a horizontal line, fictitious, that we're going to put across all the heights of our heads, right? And we're going to lower or raise that line to the point that the difference between the line, whether it's below my head height or above it, and that squared difference, so it's going to be maybe right here, so the squared differences across all of us is minimized. All right, so we're just going to take that line. The computer does it for us. It moves it up or down so that the sum of all those is minimal. Wherever that ends up is our estimate of x, which will be a height measured from the floor. Okay, maximum likelihood is going to do something very different. Okay, what it's going to do is going to say, all right, now I want you to imagine height on the x scale. Okay, so we're going to arrange ourselves from let's see, from your perspective, smallest x over there to largest x over here. So we need to do that. So you're going to be on the small end of the x, right? You win that prize. And so we're going to do increasing. Do I win?
I think you win. Yeah.
No, okay. I wasn't winning. Lose, I mean. Did I lose? Okay. So do we look like we're increasing height now? Okay. So now what you have to imagine is a distribution. So the distribution, imagine over, instead of the line now, the distribution goes up, over, and all the way over here. I represent someone that is on from this sample on the higher end of the height distribution, so u, and on that end we have the lower end of the height distribution. The mean x is now on this horizontal scale, right? The mean x height is going to be a vertical line somewhere on that distribution. The way maximum likelihood works is we're going to assume a distribution. Let's assume normality, right, that we're drawn from a normal population. And the way that works is the distribution in your mind's eye now is going to be shifted to the left or to the right such that the average value fits over us to maximize the likelihood. So how does the likelihood calculate it? Well, that distribution, if you shift it, the height of the distribution is actually the proportional to the probability, right? Imagine a distribution. So when we shift the distribution, I can see where I sit. So we would actually order ourselves such that we were on a linear x scale. So do you get me? So we're ordered now. We're ordinal now, but we're not ratio now. We probably would need to be ratio. Okay? And I can shift that distribution so it can calculate the probability of me in this distribution, and in you in the distribution, and you and you and you. And we can shift the distribution around for each individual to maximize the probability of observation. That is, we shift the distribution around such that the probability of observing all of us is maximized. Okay? And we'll just shift it back and forth until we find that maximum, and then the center of that, the median, is where our estimate of x is. Very different approaches, right? Very different approaches. One's shifting a distribution around. One is just moving a line up and down. The thing to note is that in the ordinary least squares, we didn't make any assumptions about distributions whatsoever. Just ordinals minimize fit distances. But in this, and maximum likelihood, we had to assume a distribution for it to work. Because we can't calculate the likelihoods without a distribution to calculate a likelihood too. So, and thank you very much for helping me with that. So that's the fundamental difference between the two estimation approaches. If you remember that, you'll always remember how it's done. You're assuming a distribution. You're looking at your observed sample, and you're shifting that distribution and then calculating the probability of observing that sample, and shifting it around to maximize it. So in principle, so we want to find, so we have a bunch of samples y's. We want to find the value of the estimator beta hat that most likely to generate the sample. And this is exactly what I just showed. You have a distribution. You have a bunch of samples below y1, 6, 3, 5, 2, 4, and you're shifting that distribution around. Clearly from that picture, the distribution on the left probably would have higher likelihood than the distribution on the right, right? How do I say that? Well, look, if you look at y1, the distribution on the left, the probability is somewhere in that 20% range, a pretty high probability, right? Whereas y1 on the right distribution is down in that small tail, so it has a small probability. So that's what's happening. We shift around to maximize those, and the y's would be on the linear scale, on the ratio scale, so they'd be ordered such that precisely on the scale that they were measured. And ordinary squares, that y is normally distributed with mean, beta, and variance. Therefore, the probability distribution is written as this. So this is the normal density. So we make an assumption. All of the maximum likelihood models we'll look at will make an assumption about the distribution. Often it's normal, but it's not always. So the important thing to note is that we have a likelihood function. And that was your question earlier about L being the likelihood function. Now we're defining it. So the likelihood function, and I want you to conceptually think of all of us up here again, is is all of the probability of all of the individuals in the sample multiplied by each other. So if I go back to that chart, the 0.2 for that y1 times the whatever the probability for y4 and multiplied together, you maximize that function. If you realize, if you think about that for a second, the larger are the numbers, the probabilities for all of those, the larger that the product of those probabilities will be. Okay? So, and it turns out that so in this case it's a product of probabilities. It turns out mathematically that the likelihood is mathematically difficult to work with. So what we'll see in all of our models is the log of the likelihood, or LL. So the log of the likelihood is mathematically much better to work with. And so if the likelihood, what is the possible values of a likelihood function? That is the product of probabilities of everyone multiplied together. Anyone know intuitively what the range of that possible values would be? 0 to 1. Very good. So the log of the likelihood then, negative infinity to 0. Right? But we will never reach 0. So a better model has a higher likelihood function, which would be a value closer to 1, then a better model on the log likelihood would be closer to 0, right? Or the least negative number, the least negative log likelihood number. And so we do the same thing we did before. We take partial derivatives with respect to solve our equations. And we end up with, interestingly, the same exact result as we had for ordinary least squares. Statisticians have already said that maximum likelihood estimators and ordinary least squares estimators are both blue, and they both actually, under the right conditions, collapse to the same set of equations for linear regression. So it's a very good result. And so again, it turns out, but not in all the models we look at, but in the linear regression case, maximum likelihood and ordinary least squares are both blue. Any guesses about which set of algorithms is easier to do in a computer model? In a computer, like Excel code, maximum likelihood or ordinary least squares? Yeah, ordinary least squares is easier because it's just, because you don't have to bring in this complicated distribution function and into the problem solving. So it is. It's quicker. Okay, properties of maximum likelihood estimators. They're consistent, beautiful. They are asymptotically normal, wonderful. They are asymptotically efficient, and the maximum likelihood estimators are not generally unbiased or efficient. So they're not always unbiased. So we might have some biased estimators sometimes, and we'll have to live with that. And we'll see cases in our class when that's the case. All right. Gosh, why I gotta stop it from doing that. All right. So we're going to get to our first assignment. Okay. So I'm gonna walk you through that, and then. Yes.
Like when you were showing the example, you said that you would be using a distribution and that you could
Yes.
go left or right, and since that the likelihood is maximum. Now, what I understand is in addition to shifting it left or right, we can also expand it or contract it. So when you're doing the maximum likelihood estimate, when we calculate the likelihood, we also maximize or minimize for the variance, right?
Yes.
And that variance is also calculated simultaneously. It's a simultaneous process.
Yes. So thank you for raising that. So the normal distribution has two parameters, a mean and a variance. And in my example, I was focused on the mean because the parameter I was talking about was the mean. But when you fit a distribution, you also have a variance of that distribution. And so you have to not only shift the distribution, but you have to shape it as well. You'll have to estimate a variance that makes sense. And so you will do that. And you'll estimate both parameters of the distribution in the fit. And you'll see in all of our models, we have estimates of variance, or epsilon, in our models. And so those will be related. But yes, it's a good point. In the ordinary least squares, we also have an estimate of variance, but not of the distribution of the ordinary least squares. But to make inference, we make the additional step of inferring or assuming that the residuals are approximately normally distributed. And then we'll have to estimate a variance of that normal distribution. And that's how we make inference, is by assuming the residuals are normally distributed. Okay. Let's look at, we're going to go to, and so what we're going to do, I'll describe the lab, and then we'll get on the computers, and I'll walk you through getting the software going. And as I saw on a base of hands showing, this is the first introduction for many of you to LIMDEP software. So I recognize it will take some time, and some of you are going to have to move to get access to a computer if you can, or to pair up. And we'll see. And tomorrow, I think everyone's going to bring in their own laptops. And how did you distribute the software? You just okay, you've got it. Okay. All right. So let me describe it, and then what I'm going to do is I'm going to get up here on my computer, and I will kind of show you up here. I'll walk you through LIMDEP and getting you sort of oriented with LIMDEP, and show you how the software works a little bit, and go from there. All right. We're going to do a linear regression model to start, just to get used to LIMDEP and to talk about linear regression modeling and to start us off. So we start big picture, getting down to a simple model, and then we're going to get more complicated as we go through. It's going to be a model of average driving speed in miles per hour. Okay, so we had 151 commuters driving in State College, Pennsylvania in the spring of 1986. So fairly old data. Data set with 13 variables in it. And you'll see the data in a minute. What we want to watch for in this, and this is going to be a good example, we're going to start wondering about endogenous variables. And I think some of you might get tricked or tripped up into putting an endogenous variable in the model. And if you don't, then I'll ask you to do so, and you'll see what happens. And we can talk about that and see and discuss why it happened as it did. But let's just see how that unfolds and see what happens there. But it'll be something we'll want to look at. We also might get into the treating unordered data as ordered, and significant t-stats, improving corrected R-squared. So the corrected R-squared is the penalized measure of fit. So that was a question you asked, I think, about how complicated we get the model, right? So we want a penalized measure of fit. And the adjusted R-squared does that. So it penalizes us by having a more complex model and allows us to say, that R-squared got worse. All right, so real quick, how many people have not been exposed to R-squared or goodness of fit, model goodness of fit measures, and would like me to review that? I'm happy to review it, and we should talk about it before we dive into it, because I can do it very quickly. Okay, let me ask the other way. What's that? Yeah, how many people know really, really well R squared and goodness of fit measures and feel confident that they can get up here and teach it? All right, that's a good thing to go on. I'll just share with you conceptually what the R squared is, and because it's actually conceptually, if you understand it, is really, really good. Okay. Goodness of fit measures, and there's a number of them. We'll see them in our models as we go through. It's meant where they're called by statisticians are called omnibus tests. So as you know, we'll have measures of how good the variables are in the models. We'll have t-stats, and we'll talk about those in our assignment. We'll spend some time getting everyone back on the same page about how we assess variables. But those are individual variables. But an omnibus is sort of an entire model test that says how good is the model performing. R square is one of those measures that we use to assess the overall performance of the model. I want to make it very clear that R square is not good or bad. A student asked me just last week, I estimated a model and it only had an R square of 12%. Does that mean it's a bad model? And my answer is absolutely not. It doesn't mean it's a bad model. You can have good models that are 12% R squared. You can have good models that are 5% R squared, and terrible models that are 90% R squared. It's not about R squared that determines how good a model is or not. So R squared is simply a reflection of how much of the overall variability in Y, in the outcome, is captured by the variables you have in your model. Okay? And I'm going to intuitively describe what happens. Okay? So in 2 dimensions. Remember, if you have 2 dimensions, we have a y-axis and an x-axis. Okay? We have a scatter of points, and usually the scatter of points is something we fit a line through. Okay? I'm going to use my arm as that line. Now, intuitively, I want you to understand, if, let's say the line is here, our fitted line, the more scattered the points are around the line, the lower is R squared. So if the points are scattered really tightly around the line, the R squared goes up. The other one that's not so intuitive, but will be after I tell you, is the steeper is this line, R squared goes up. The more and more steep the line, the higher is R squared. And as it goes down and down and down, and if it gets to flat, what is flat? R squared. 0. R squared is 0 when the line is flat. So it can only, and then it goes from 0 to something very small. And so those 2 are the 2 things that act on R squared. The steepness of the line and the scatter around the line. Those are the only 2 things that affect it. All right? Yeah.
Does that mean if there is a line is horizontal, so any change in x won't change y?
That's right.
That means no variability is being captured by that x.
That's exactly right. So the conclusion is if you had a flat line, it means x has no impact on y whatsoever. X should not be in your model. Because x does not matter. And x would be an irrelevant variable and adding noise to your model when it should not be. We don't want noise in the model. So that's exactly right. All right, so those are the 2 things that affect goodness of fit. And so R squared sits between 0 and 1, 1 being perfect fit. So 1 would be a very steep line and everything on the line. Right? We actually don't ever get that. Never get to 1 because then it's deterministic. But we can get very close. So you can have a steep line and just very tight fit around it. That would be, could get a very high R squared. But the question about what high R square is good or bad is only relative to what other people have done and other models you've estimated and around the phenomenon you're studying. So if the best anyone has ever done in studying some phenomena is 5%, and you collect a few new variables and you come up with a model at 6 or 7%, hey, you've discovered a new part of that process that was unknown. And even though 7 seems like a low number, it's probably a really good model. And similarly, you could be at 90%, but the variables make no sense. You can't explain them to people, yet you get a good fit. And it could be coincidence that you have these variables in the model, and it's not a good model. So R squared itself is not a value that tells you whether a model is good or not. It just helps you decide among competing models and where you are relative to understanding this phenomenon. Okay? So that's a very quick review of R squared. So we use that as a measure of overall goodness of fit. And the corrected measure will allow it to go down if you get to make a complicated model. That's what the penalized measure of fit is. All right. So what they did is, so let me explain. So what happened is these 151 commuters commuted from this rural location. Boy, those arrows aren't showing up very well. I think the arterial should be shifted over to the right, so that Alberton Street. But there was a rural road and into town from this complex, a freeway and an arterial. And so people had a speed that they drove along these routes into College Station. And so what we're going to be looking at is what happened and trying to model speed. Okay, so here are the variables. Number of lanes that were on the routes that they selected. Hourly capacity of the most restrictive section, so the pinch point, if you will, of the routes in vehicles per hour. The average point-to-point distance, okay. Average travel speed in miles per hour, okay. The average travel time in minutes. The ratio of the highest observed travel time to free flow travel time. So what is that last one capturing for those of you not in the traffic space? The highest observed travel time to the free flow. So we're looking at how much congestion, right? A measure of congestion. Okay, so we have the data here, and there's a reference there on this model if we want to. Okay, so now let me switch over, and I will get LimDep up, and we will load LimDep into, and so hopefully we'll go through together and get you all up to speed on LimDep. Any questions before I leave this, and we'll start to go into LimDep. Okay. So I think a number of you told me that when I asked about use of LimDep, only a few hands went up. So just to tell you briefly, LimDep is written by William Green, who is just retired. In fact, I got invited to his retirement party in New York, but because I'm in Australia, wasn't able to go. But he is, I think, one of the most highly cited econometricians in the world. And I lost track of his H index. I think it's nearly 100 or something. But his book, it was one of those books that everyone used all around the world, and it's this fat, unreadable text. If anyone looked at it, it's really, really hard. But he teaches so the other thing that happened is another researcher in transport joined his software team, David Hensher from Australia at the University of Sydney. And so joined with Bill Green and had Bill modify and improve the software to focus on transport and develop a suite of modules that supported discrete choice models, which we will do in this class. And so they do all kinds of econometrics, but as well as discrete choice. And they've been improved over the years, but there are still some bugs here and there, and the software still does some weird things sometimes. So it is that way. All right. So this is what your software looks like, and I would hope you would all open your software and see what it looks like. Let me just walk you through a few things. So the way it works is we have a few command files, and we'll open data, and I'll pull the data in. But we open data. There's various ways we can run LIMDEP. There's the pull-down menus you can see here. So you can see, for example, model. These are all grayed out right now, but once we have data in there, we can pull down menu, and we'll have a bunch of menu-driven options to specify models. You will quickly learn that that's not an efficient way to use the software. So the other way to do is a command line sequence, and we'll do everything command line here. I might illustrate a couple times of the pull-down menus, but we'll do command lines to install, to run programs. And it's very easy to just slightly modify command line sequence to estimate a different model. And you'll get the hang of it very, very quickly. So, and you can run it in batch mode if you get really good and do all things and things like that. So now I'm going to find the file. So you should have data files, right? Does everyone?
Simon,
Yep.
now you can just show it in your computer.
Okay.
Probably I think they will not share the data file. But
Okay.
this afternoon, I think, since some of the research scholars already know this LIMDEP, so I think they can sit and show the first data file that
Okay. Okay.
I think, you can show the steps, and maybe in the afternoon they can do it with the data file. Will that work?
Yeah, we can make that work, but are you okay with that?
Well, yeah. I mean, that's fine. We can do this first lab.
Share the data file with them.
Okay. 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 So. So there's three different. So what we'll have is the lectures which you have printed in your manuals, and then you do have at the back of your books the lab descriptions. So so you should be able to go to lab number 1 and the first one, page 77, and you'll see the first exercise. All right. So we'll do this together then, and we'll walk through it. Okay, so this is the first lab exercise. And what I've done, and all of the lab exercises, is I've given you command lines, okay, to enter into LIMDEP. So here are the data again. So there's actually some data that show up in this that didn't show up on there. So here are the raw data and the data files that you have. You have number of traffic signals on the selected route, whether seat belts were worn or not, number of passengers in the car, the driver age, the driver gender, the marital status of the driver, number of children, annual income, model year of the car, and the car origin. So you can see there's lots of information here about the individuals that make decisions to take different routes. You can see X2 is the route chosen, 1 being arterial, 2 being rural road, and 3 being freeway. What's the scale of that variable? X2. What's the scale of X2? Nominal, right? Yep. Nominal, right? Yep, we should, yep. And so, and and you'll see, and I'll probably just refresh. Some of this is refreshing your memory. Some of this is new. But a variable like x6 is what we'd call an indicator variable, right? We have a lot of times we'll use indicator variables where it's take on the value 0 or 1. We don't want indicators variables to take on the value 1s or 2s, all right? Because we'll talk about it implies a numeric has a numeric implication, so we want 0s or 1s. 0 meaning it just goes away if they're not a certain condition, and 1 if they're in a certain condition. So we'll see all indicator variables are always coded as 0s or 1s. Okay, there was a question?
So you said x2 is nominal variable.
Yes.
But I mean, just a question that if the node is a name, but there are speed associated with it, like arterial freeway will have maximum speed and
Yes.
so is it like ordinal or?
No. So it's a good question, though. It's a good question because you're absolutely correct that because they they have speeds, there's some order, but the speed has order. The speeds is a continuous variable ratio, but x2 is nominal because all it describes is a category of facility. Yes, speed they have then, but what if you counted? What if you said, well, but the number of trees goes up with rural, and that's larger for real. So maybe so it's not that other attribute associated with the variable that matters. It's the variable itself that matters. So, and they're just categories of type of facility. But it's a good point. You're absolutely right. They have implications underlying that there's the increasing speed associated with those. But that's a second attribute associated. And what you point out, though, is that correlation is going to be there. That is important. Those have implications about speed and implications about signals and implications about probably pavement quality and a lot of other things. Do we have pavement quality on there? No. So pavement quality might be an omitted variable if pavement quality matters. Interestingly, so those are the kinds of questions we need to ask with data. What's omitted, what matters, and that's and I'm glad you raised that made the point because this when we go through these kinds of things, these kinds of questions are so important. Well, what do we expect to find? If we do good research, what would we think would matter in people's speed selection? We need to know that before we can understand what variables we should collect. We're just stuck. We go straight to the end. And we make assumptions about a lot of things that were made in the design of this study. Did you have another question?
Again, the same thing. Like, ordinal data would be a nominal. I mean, it will be named, but with a certain order, right?
Yes.
Ordinal data.
Yes. Like crash severity. Yes.
So basically, these are also names with an order. I mean, if we say that strongly disagree is an order.
Yes.
Then similarly, freeway, arterial is an order. So we are not talking about speed, but inherently we want to capture the speed as such in this case.
So in the crash severity variable, if we had a crash severity, I know there's order because I'm talking about its severity. The variable itself is about severity. But this is just about facility type. It's not facility speed. If I had a variable called facility speed and called them arterial, rural road, and freeway, I would agree with you. But I'm calling them facility type. Because I've called them facility type, speed is a separate variable on its own. And so I think I'd have to rephrase it, but it's a fine line. And you're raising that point. There's a fine line there, but yes, comment, yeah.
I'm talking about another example. If we consider carriageway configuration, like how many numbers of lanes are there in a particular stretch? Like
Yes.
it may be 1 lane road, 2 lane road,
Yes?
So, means what should we consider? Like the number of lanes in each direction, is whether it is a nominal variable or the scale.
So number of lanes would be a ratio scale variable because it has absolute 0, and we know that the division between 1 and 2 lanes is clear. And although I have to confess, less clear in India than it is in the Western world. But you know, in this concept, right? It's clear. So it would be a ratio variable in that case. Yeah.
So in case of H2 variable, we have 3 class, arterial row and freeway.
Yes.
So we are just numbering it 1, 2, and 3.
Okay.
So we can number it in any way. So definitely. If
Yes.
the number is 0, 1, 2, will it be correct?
Okay. These are all really good questions. So I've got numbers on X2, 1, 2, and 3, which implies the ordering, right? You often get data that are numbered for you. I don't care what somebody's number. We need to know what that is, and it's ordinal. So I'm going to deal with the 1, 2, and 3 the way it needs to be dealt with. I won't code it as a 1, 2, 3. I can't code it as a 1, 2, 3 and leave it like that because that would imply there's order. And so that would be problematic. So those are all the kinds of questions we need to make sure that all the data are coded the right way and are contained in the right and reflected and captured the right way. Otherwise, we can run into troubles. So all of these questions are absolutely spot on. It's about understanding what the scales of the variables are, how we should code them. So as Sudeshna mentioned, we typically would code that as indicator. That it's a 1 or 0. If it was on the arterial, a 1 or 0 if it was on the rural road, and a 1 or 0 if it was on the freeway. And that's how we would treat those. 0, 1s is nominal. And in fact, almost always nominal variables, when they're on the right-hand side, are treated that way, as 0 or 1s. That's almost a dead giveaway of how we would treat a nominal scale variable. We don't want to give them order when they don't have it. So a great comments. Anything else before I leave the data? So keep these in mind because when we estimate models, we'll look at these. All right. Yep. X13. Model year of car. Yes. How are we going to deal with that? Does model year of car, if we used it like it was coded there, would that be useful, do you think? Leaving it coded as an 86. If you, yes. Good. So you're right. It's problematic if you leave it as an 86. Wow, what does that mean? You know, how you put something as an 86, but if you convert it to age of the car, then that's going to be useful. Age of the car when? From now? So we take 2018 and subtract 86, or yeah, 1986, or at the time of the study. Right? All this stuff you have to get right. You have to think about it. All right. So here's what we've got. If you look at these two codes, what I'm going to do is I'm going to modify this to read in. So we've got these commands, and I'm going to show you how we do this. So I'm going to do this one at a time just so you can see. So we've got these codes, and I'm going to go into LIMDEP. And I'll new command document. All right, so this is where we can run commands. And I'm going to copy these, and so now it's going to want to read this file. So the main thing to recognize is that we have to tell it exactly where it is. And if I try to run this, it's going to give me an error because it's not the right location. So on this computer. So that's a command from a previous one. So I need to figure out where these files are exactly. And that's the location. It's much longer and more complicated, right? Actually, that's not location. It's that's not it either. It's IT lab files. That's the location. So, and there's this C drive, I think. I think it's going to be that's going to be interesting. I might have to move it to the desktop, I think. I don't think that's going to work. So just to show you, when we run lambda files, there's a number of ways we can do it. But if you can highlight the command and hit run. And it kind of looks like it did it. Okay. We'll find out very quickly. Now, if we'll click on variables, and if it did read the file, which I didn't think it would because it's too complicated of a location, that'll open up a new window with all the variables in it. So normally what we do is have all the commands open it together. So you can have, when we run this, we can have a command window and an output window and a variables window. And so what I'm going to do quickly, just to make this go quicker, is I'm going to take our first file. And put it on the desktop. Make this much quicker. So here's the location. All right, so this is the command line, the command panel, and we're going to change this. Yeah. Oh, really?
Yeah. So I think this, since it is a tutorial.
Yep.
And I think maybe we need to continue it post lunch.
Okay. Okay. In this room or somewhere else?
Somewhere else.
Okay. Do you have somewhere else?
Yeah, I
Okay.
have.
Okay. Okay. All right. Yeah, that's fine. Yeah. Will we be able to display it at the other place, the location?
Yes.
Yeah.
The
Okay.
projector is there.
Yeah. Okay.
Projector is there.
Okay.
So maybe we conflict and then
Okay.
from
All right.
this
Okay. So I have the official word from my boss that that we are going to have lunch, break for lunch, and then we're going to do this tutorial in the afternoon, and then would it be possible to then to get the files distributed, and
Yes,
so we could, okay, because that would be much better if we can get everyone going. Okay, perfect. So we're breaking for lunch. I think we're not coming back to this room, right?